Hello everyone and welcome back to CSEN701 Embedded Systems Architecture, also known as Real-Time Embedded Systems. Today we are going to discuss tutorial 6, which tackles the real-time operating systems scheduling algorithms. Mainly we will be discussing two algorithms. The first one belongs to the static priority scheduling algorithms family, which is the rate monotonic, also known as the RM scheduling algorithm, and the second algorithm belongs to the dynamic priority scheduling algorithms family, which is the earliest deadline first. And as you all know, this tutorial is given on campus to all groups. So if you missed this tutorial on campus, you can watch the video. Before we start, let me tell you why do we need scheduling algorithms in the context of real-time operating systems. As you all know, we have a scheduler which is responsible for selecting which task to run. The scheduler uses a scheduling policy or a scheduling algorithm to assign some priorities to the tasks present in the system. So actually, we need a scheduling algorithm to assign priorities to the tasks so the scheduler can select the task with a higher priority to what to run. And in the context of real-time operating systems, our tasks have deadlines. So we need to make sure that all tasks meet their respective deadlines. And as I told you before, we have two categories of scheduling algorithms. We have a static scheduling algorithms category and we have a dynamic scheduling algorithms category. And let's start with the static priority scheduling algorithms. Hello everyone and welcome back to CSEN701 Embedded Systems Architecture, also known as Real-Time Embedded Systems. Today we are going to discuss tutorial 6, which tackles the real-time operating systems scheduling algorithms. Mainly we are going to tackle two algorithms. The first one belongs to the static scheduling algorithms family, which is the rate monotonic, also referred to as RM, and the second algorithm belongs to the dynamic scheduling algorithms family, which is the earliest deadline first, also known as EDF. And for this category of scheduling algorithms, we will be discussing the rate monotonic, also known as the RM scheduling algorithm. The rate monotonic is an optimal static priority scheduling algorithm. What is the meaning of an optimal static priority scheduling algorithm? It means that if there is any other static priority scheduling algorithm that can meet all of the deadlines, then the rate monotonic scheduling algorithm will also meet all of the deadlines. Meaning that if I have a set of tasks that is schedulable by any other static priority scheduling algorithm, then it will also be schedulable by the rate monotonic scheduling algorithm. Therefore, the rate monotonic is what? It's an optimal algorithm. Okay, if any other algorithm which belongs to the static priority scheduling algorithms can schedule a group of tasks or a set of tasks, then the rate monotonic can also schedule the same exact group or set of tasks. And when I say, for example, a group of tasks is schedulable under rate monotonic or under any algorithm, this means that this algorithm or the rate monotonic algorithm makes sure that all of the tasks present in the set or in this group meet their respective deadlines when executing. Okay, so let's have a quick recap on RM or rate monotonic and how does it work. Actually, rate monotonic assigns priorities according to this mechanism, which is the task with a shorter period will have a higher priority. So if I have two tasks in a system, task 1 with period 5 cycles and task 2 with period 10 cycles, task 1 will be assigned a higher priority than task 2 because task 1 has a shorter period compared to task 2. And actually, it's a static priority algorithm because if I have a system which consists of 5 tasks, I'm not adding any additional task, I only have 5 tasks in the system. Before I run the system, the rate monotonic will assign priorities to all of the 5 tasks according to the period of the 5 tasks. And if I say, for example, a task has a period of 5 clock ticks, for example, if my unit of time is clock ticks, so I say a task has a period of 5 clock ticks, this means that every 5 clock ticks, a new instance of this task will enter the system. Okay, and when it enters the system, it definitely wants to execute to meet its deadline. So now let's start with our first example and question 1. We have here 3 tasks in the system and we are given their period and the worst case execution time, which is WCET. And the period here will be in terms of clock ticks, not cycles, not seconds. It will be in terms of clock ticks. Okay, we have task A with a period of 25 clock ticks and a worst case execution time 6 clock ticks. This means that when task A enters the system, it actually needs 6 clock ticks to finish executing. However, it will return again to the system after 25 clock ticks. So I need to actually execute this task, task A, before it re-enters the system with a new instance. We have also task B with a period of 20 clock ticks and a worst case execution time 5 clock ticks. This means that every 20 clock ticks, I need to execute task B, and task B actually needs only 5 clock ticks to finish executing. And this is the worst case execution time. So actually here we take into consideration the worst case scenario. Finally, we have task C with a period of 15 clock ticks and a worst case execution time of 5 clock ticks. So it needs 5 clock ticks to finish executing. However, it will again return to the system, or it will return to the system again after 15 clock ticks. Now, the question states, using the utilization bound or the UB test, can we draw conclusions about the schedulability of the set under rate monotonic or RM? So, in order for us to know whether this group of tasks, which is task A, task B, and task C, is schedulable under RM, can RM make sure that all of these tasks will finish executing before their deadlines and before the return of a new instance to the system? We need to perform some tests, and these tests are theoretical tests. Okay, they are calculation based tests. We have two main tests. The first one is the UB test, which is the easier test, and the second one is the response time test. In this question, it asked for the utilization bound, and the utilization bound, although it is an easy test, however, there is one condition that must be satisfied in order for us to use the utilization bound test to actually check whether this set of tasks is schedulable under rate monotonic or not. The condition is that the deadline must be equal to the period of the tasks. So here, the question did not specify a particular deadline for each task. Therefore, the default assumption will be that the deadline is equal to the period. So if task A has a period of 25 clock ticks, this means that the deadline is also 25 clock ticks. So if this task enters to the system, I have 25 clock ticks in order to execute and finish executing this task, or else I will miss the deadline. Okay, so for us to use the utilization bound test, we need to make sure that the deadline is equal to the period. The deadline must be equal to the period. If it is a different number than the period, a different clock ticks other than the period, then we cannot use the utilization bound test. So how does the utilization bound work? The UB test for RM is the summation of the utilizations, and the utilization is actually calculated as the computation time divided by the period for each task. So actually we want to sum the utilization of all 3 tasks present in this set, and the utilization is the computation time, which is the execution time, divided by the period of the task. So here, for task A to calculate its utilization, the computation time is 6 divided by the period is 25. For task B, the computation time is 5 divided by the period, which is 20. And finally, for task C, the computation time is 5 divided by the period, which is 15. Okay, so to calculate the summation of the utilization, we'll be adding 6 divided by 25 plus 5 divided by 20 plus 5 divided by 15. This summation must be less than or equal to n multiplied by 2 to the power of 1 divided by n minus 1. And here n denotes the number of tasks present in the system. So in our system, we have 3 tasks, A, B, and C. Therefore, n will be equal to 3. So if we calculate 3 multiplied by 2 to the power of 1 divided by 3 minus 1. Okay, this will result in 0.779, and this we call the threshold. Okay, so actually I calculated the summation of the utilizations and I calculated the threshold. The summation of the utilizations must be less than or equal to the threshold. So the summation of the utilizations, 6 divided by 25 plus 5 divided by 20 plus 5 divided by 15 is equal to 0.82. Is 0.82 less than or equal to 0.779? No. Therefore, we have a problem. The problem is that this set of tasks may not be schedulable under rate monotonic. However, this conclusion is not 100% accurate. So our answer will be it is inconclusive. I cannot guarantee that this set is schedulable under RM. However, I cannot also guarantee that it is not schedulable under RM. And this is the trick about the utilization bound test for the rate monotonic algorithm. We have 3 scenarios the utilization bound can result. The first scenario is that the summation of the utilization of the tasks is actually less than or equal to the threshold. If it is the case, then we are 100% sure that this set of tasks is schedulable under RM. If the summation of the utilizations is less than or equal to the threshold, then it is 100% schedulable under RM. However, if the summation of the utilization is greater than the threshold, however, less than or equal to 1, then it is inconclusive. Because this threshold, or actually the utilization bound, is used to determine the CPU resources that you need, the percentage that you want to use from the CPU. Okay, to actually, if I have a CPU, then I have 100% of resources, which is 1. If actually the summation of the utilization is greater than the threshold, however, it is less than or equal to 1, this means that you do not need more than 100% of the resources of the CPU. However, the rate monotonic cannot actually access or use 100% of the resources of the CPU for this group of tasks. Okay, therefore we have a threshold. This threshold means that the rate monotonic can actually use this percentage of the CPU. In our case, if we have 3 tasks in our system, then the rate monotonic can use 0.779, which is 77.9% of the CPU. So if you are actually less than or equal to this number, you are on the safe side and you are 100% sure that the rate monotonic algorithm can schedule the tasks and all of the tasks will meet their respective deadlines. However, if the summation of the utilization is greater than the threshold, but it is less than or equal to 1, which means 100% of the CPU utilization or the CPU resources, then it is indecisive, it is inconclusive. It may get scheduled and it may not get scheduled. We do not know whether the RM can actually schedule this set of tasks or not. We need to perform another test to make sure that the rate monotonic can actually schedule them or not. Okay, because the UB test is a shortcut test to actually determine if it is schedulable or not. If it is schedulable, then it is 100% schedulable. If it is less than or it is greater than the threshold, then we cannot determine using the UB test. We need to actually use the response time test to see whether it will be schedulable under RM or not. Therefore, in this case, it is inconclusive because it is greater than the threshold, but it is less than or equal to 1. However, if the summation of the utilization is greater than 1, greater than 100%, then this means an overload will occur, meaning that you need more than 100% of the CPU resources, which is impossible. Therefore, it is not schedulable under RM. So if the summation of the utilization was actually more than or greater than 1, it is 100% not schedulable. If it is less than or equal to the threshold, it is 100% schedulable. If it is in between greater than the threshold but less than or equal to 1, then it is inconclusive. It may get scheduled or it may not get scheduled. The UB test cannot determine. Okay, the utilization bound cannot determine, because the utilization bound only figured out a percentage, a safe percentage, which is the threshold, in our case 77.9%, that the RM can 100% access. However, if it is more than this threshold but less than or equal to 1, then there are other factors that determine whether this task can be scheduled under RM or not, and we need to perform another test to make sure that this task can be scheduled or it will not be scheduled under RM. Therefore, here, since it is 0.82, which is greater than 0.779, however, it is less than or equal to 1, then it is inconclusive. I cannot determine or say whether this task or this set of tasks is schedulable or not schedulable. I cannot say. I cannot for sure guarantee that it will not be schedulable. Who knows? It may be schedulable, because the threshold is not 100% of what of the CPU utilization. It is just 77.9%. Okay? Let's move on to the second part of the question. Draw the execution diagram in a window of 80 clock ticks of the above set using the RM scheduling algorithm. So actually want to draw a window of 80 clock ticks, and let's see the execution of the tasks and which task will be executed when. So first of all, we need to assign priorities to the 3 tasks. And since we are using the rate monotonic scheduling algorithm, therefore the priorities are assigned according to the period of the tasks. The task with a shorter period will get a higher priority. Here we have 3 tasks and 3 periods. The shortest period is 15 clock ticks, which is task C. Therefore, task C will be assigned the highest priority in our system. Let's see the second shortest period. It is 20, which is the period of task B. It is 20 clock ticks. Therefore, it is the second shortest period. Therefore, task B will be assigned the second highest priority in the system. Finally, the lowest priority in the system will be assigned to task A, because it has the longest period in the system, which is 25 clock ticks. So in RM, we assign priorities according to the period. The shorter the period, the higher the priority. Task C had the shortest period in the system, 15 clock ticks. Therefore, task C was assigned with the highest priority. Task B has the second shortest period in the system with 20 clock ticks. Therefore, it was assigned the medium priority, which is the second highest priority in the system. Finally, task A had the longest period. Therefore, it was assigned with the lowest priority. So, if the question did not actually state the arrival time of each task, we use the default assumption. And the default assumption is that all 3 tasks arrived at the same particular time, which is clock tick 0. Okay, because the question did not actually state arrival times, therefore we use the default assumption that all tasks arrived at the same particular time, which is clock tick 0. And actually we denote, or actually we identify or represent the arrival time of the tasks with an upwards arrow. So let's actually draw the execution diagram. So if we go to our sketchbook to draw the execution diagram, we have 3 tasks, and as I told you before, the question did not specify the arrival time of the tasks. Therefore, all 3 tasks arrived at the same time, which is at the 0 clock tick. Okay, we have here task A, we have here task B, and finally we have here task C. right? And to represent the arrival time of a task, we draw an upwards arrow. And it's a must to draw the upwards arrow. Okay, so actually an upwards arrow represent the arrival of a task. And since all tasks arrived at the same time at clock tick 0, therefore we drew 3 upward arrows, one for each task. Okay, if we remember the properties of the tasks, we had task A, a period of 25 clock ticks, and it had an execution time of 6, or a worst case execution time of 6. We had task B, period of 20, and execution time of 5. And finally, we have C, a period of 15, and an execution time of 5. And we click OK, and we move this to the side. Therefore, the highest priority task will be C because it has the lowest or the shortest period. And since all 3 tasks arrived at the same clock tick, the highest priority task will execute or it will run. The scheduler will choose the highest priority task to move from the ready state to the running state. So we have task C will run, and it will need 5 clock ticks to run from 0 to 5. Okay, we needed 5 out of 5, or we executed actually 5 out of 5. So at clock tick 0, task ABC arrived to the system. C had the highest priority because it had the shortest period. Therefore, task C will execute first. And actually, since it is the highest priority task, so it will execute for the full 5 clock ticks it needs to finish executing. So if a task needs 5 clock ticks to finish executing, and it actually took 5 clock ticks, or it was running for 5 clock ticks, this means that it finally finished executing like task C, and to represent this state of that a task finished executing, we draw a downwards arrow, and it's a must to draw the downwards arrow in the exam, or you will lose marks. Okay, so actually task C needed 5 clock ticks. It ran for 5 clock ticks, or it executed for 5 clock ticks. This means that it finished everything it wanted to do. Therefore, we drew the downward arrows to represent that a task finished executing. Okay, then task C will return back to the system at clock tick 15 because its period is 15. So at clock tick 15, task C will return back to the system. For now, we are at clock tick 5 and task C finished executing. We have 2 remaining tasks, A and B. Task B has a higher priority than task A because task B has the shortest period. Task's B period is 20, while task A period is 25. Therefore, task B will run, and it needs 5 clock ticks to run. So let's choose a different color, for example, blue. Here, okay, at clock tick 5, task B will execute for 5 clock ticks. And here, this will be 10. Okay, so it used 5 out of 5, or it actually spent 5 clock ticks running, and it needed 5 clock ticks running, so it finished execution. Therefore, we draw a downwards arrow. Okay, so here at clock tick number 5, task C finished executing. Thus, task C will return back to the system here at task 15, at clock tick 15. So at clock tick 15, task C will return back to the system. So before it returns back to the system and runs again, because it is the highest priority task, we have 2 remaining tasks, A and B. Task B will run starting from clock tick 5 because it has a higher priority than A, because the priority depends on the period, and task B has the shortest period compared to A. Its period is 20 compared to the 25 clock ticks of A. Therefore, task B will run. Task B execution time is 5 clock ticks, so it will run from clock tick 5 to clock tick 10. And it needed the 5 clock ticks, therefore it finished execution, and we drew a downwards arrow. Starting from clock tick 10, task A will execute because actually task C and task B finished. The remaining task in the system is task A. So here, task A, I mean, will run starting from clock tick 10 to clock tick 15. And it ran for 5 clock ticks out of the required 6 clock ticks. Okay, as you can see here, at clock tick 10, task A started executing. However, it needs 6 clock ticks. So at clock tick 15, it was preempted because at clock tick 15, task C returned back to the system. It returns after every 15 clock ticks. So if it arrived at clock tick 0, it will return at clock tick 15 and at clock tick 30 and at clock tick 45, etc. So at clock tick 15, task C arrived to the system. It preempts what? Task A. Task A will be preempted and task C will start executing. Therefore, task A did not finish execution. Okay? Task A did not finish execution. It has still one remaining clock tick to finish execution because it needs 6 clock ticks, and from 10 to 15 it spent 5 clock ticks. Therefore, we have a remaining 1 clock tick in order to say that task A finished execution. Therefore, we did not draw a downwards arrow. Okay, here at clock tick 15, task C will run for how many clock ticks? For 5 clock ticks. So until clock tick 20, it used 5 out of 5. Okay, and since it finished execution, we will draw a downwards arrow. Okay, so at clock tick 15, task C arrived back to the system, preempting task A. So task A did not finish executing. It has one remaining clock tick to finish executing. However, task C has a higher priority because it has the shortest period. It has a period of 15 compared to the period of 25 of A. So when task C arrived to the system, task A did not complete and task C started to execute. It needed 5 clock ticks to finish execution, so it executed from clock tick 15 to clock tick 20, taking 5 clock ticks. Therefore, we drew a downwards arrow. At clock tick 20, task B arrived back to the system. Why? Because its period is 20. So it originally arrived at 0, it will arrive at 20, it will arrive at 40, etc. So here at 20, task B arrived back to the system. Okay, so task C finished, task B arrived. The scheduler will choose task B or task A. It will choose task B. Okay, so actually task B will run for 5 clock ticks because it needs 5 clock ticks. So it will run from 20 to 25. Okay, it used 5. Why did the scheduler choose task B and not task A? Because task B has the shortest period. Task B period is 20 compared to the 25 of A. Therefore, 20 is less than 25, so the scheduler will choose task B to run. And task B ran for 5 clock ticks, I mean, and it only needed 5 clock ticks. Therefore, it finished execution and we draw a downwards arrow. At clock tick 25, which task arrived back to the system? A new instance of task A arrived back to the system. Guess what? We did not finish the previous instance of task A. It had a remaining 1 clock tick to finish executing. So task A did not finish executing before the new instance of task A returned back to the system. Therefore, as we stated, or as the UB test stated, task A is inconclusive. Okay, we cannot say that it can actually, or the RM scheduling algorithm cannot schedule all 3 tasks before the new instance arrives to the system. Yes, RM knew how to schedule task C and task B in terms of that they always finish executing before the new instance arrives to the system. However, For task A, it did not do so. Task A new instance arrived to the system before the previous instance finished execution. Therefore, it looks like that it is not schedulable under RM. So, using our eyes, the observation from this execution diagram that it is not schedulable under RM. Okay, the UB test was inconclusive. It could not say whether it is schedulable or not schedulable. However, when we drew the execution diagram, we found out that task C and task B are schedulable under RM. However, task A was not schedulable because task A did not finish executing before the new instance of task A returned back to the system. Here, at clock tick 25, task A returned to the system. However, the previous instance only executed 5 ticks out of the 6 clock ticks needed, and it did not finish executing. Therefore, we cannot find a downwards arrow because it did not finish executing. Therefore, these 3 tasks are not schedulable under RM. This set of tasks is not schedulable under RM. We knew it from what? Our observation when we drew the execution diagram. Okay, if we return back to our slides, this is the diagram, the same diagram I drew. We have task A, B, and C. An upward arrow represents that all of them arrived to the system at the same particular time at clock tick 0, because the question did not state whether when actually each task arrived to the system. Therefore, the default assumption is that all of them arrived at the same particular time, which is clock tick number 0. Task C had the highest priority because it had the shortest period. Therefore, task C started executing till clock tick number 5 because it needed 5 clock ticks. It finished executing, therefore we drew a downwards arrow. Now we have 2 tasks remaining, task A and task B. Task B will run because it has the second shortest period, which is 20 compared to the period of task A, which is 25. Therefore, task B will run for 5 clock ticks because it needs only 5 clock ticks, or its execution time is 5 clock ticks. And at clock tick 10, it finished execution. Therefore, we drew a downwards arrow. The remaining task in the system is task A, so task A will execute. However, at clock tick 15, it was preempted. Okay, task A needs 6 clock ticks to finish execution. However, it only spent 5 clock ticks out of the 6 because at clock tick 15, task C returned back to the system. It's period. Okay, it returns every 15 clock ticks. Therefore, task C returned, and the system or the scheduler preempted task A. It blocked task A and allowed task C to run instead. Since it has the shortest period, task C needs 5 clock ticks to finish execution. Therefore, it spent 5 clock ticks till clock tick number 20. It finished execution. Therefore, we drew a downwards arrow. At clock tick number 20, task B returned back to the system. Therefore, we have 2 tasks in the system, A and B. However, B has the highest priority compared to A due to the period of B being less than the period of A. 20 is less than 25. Therefore, task B will run for 5 clock ticks because its execution time is 5 clock ticks until clock tick number 25. And we drew what? A downwards arrow because task B finished execution. However, at clock tick 25, task A returned back to the system, a new instance. Okay, it's period, it's a periodic task. So a new instance of task A returned to the system at clock tick 25. However, the old instance did not finish execution. It only spent 5 out of the 6 clock ticks needed. Therefore, we can see that this group of tasks is not schedulable under RM by observation, because a new instance of task A returned back to the system before the old instance finishes its work. And take care that we knew that it is not schedulable under RM because we drew the execution diagram and we saw by our eyes that the old instance did not finish executing before the new instance arrived to the system. Okay, the UB test was inconclusive. It told us, I do not know whether it is schedulable or not schedulable. However, when we drew the execution diagram, we knew that it is not schedulable. There is another theoretical test, which is the response time, that we'll be tackling later in the tutorial, that will be 100% sure whether it will be schedulable or not schedulable under. And there is a very important note I want to say regarding this question. Okay, I said that when I was solving this question that task A did not meet its deadline because the new instance of task A arrived at clock tick 25 before the old instance finished its work. We made this assumption because the question did not specify a particular deadline for each task. Therefore, the default assumption is that the deadline is equal to the period. Therefore, when I was solving this question and when I stated that since the new instance of task A returned back to the system at clock tick 25 and before it the old instance did not finish executing, therefore it is not schedulable because here the deadline was equal to the period of the task. It's very important. In this question, the deadline of the task is equal to its period. So since task A period is 25, the deadline was also what? 25 clock ticks from the arrival of the task. Here, task A did not meet its deadline because after clock tick 25, it did not finish executing. Therefore, what? It missed the deadline. Hence, I said that since the new instance of the task arrived at clock tick 25 and the old instance did not finish executing, therefore, this set of tasks is not schedulable under RM because task A did not finish executing, meaning that it missed its deadline. Because here, and I repeat, the deadline was equal to the period. The deadline could have been before the period. For example, we may have a deadline for task A at clock tick 20. So the new instance of task A will arrive at clock tick 25. However, the deadline for task A is at clock tick 20. So if I did not finish executing task A before clock tick 20, then the set of tasks is not schedulable under RM without even waiting for task A new instance to return back at clock tick 25. Because here, the example I just stated, having the deadline before the period or less than the period. The deadline I gave, for example, for task A is at clock tick 20. However, it's periodic and it returns every 25 clock ticks. So the period was not equal to the deadline. So I actually look at the deadline, not the period. However, in this question, since the deadline was equal to the period, so I was looking at the period. Task A did not finish executing before the new instance came in, therefore it is not schedulable. However, if the deadline was not equal to the period, I will only search for the deadline. And I will say that the set of tasks is not schedulable under RM if they missed their deadline, not their period. Okay, but again, I repeat, because this question did not specify a deadline for the tasks, the default assumption, deadline equal period. Therefore, I was saying that task A did not finish executing before its period and the new instance came in, therefore it is not scheduled. Now, let's move on to the second question. And here we have also three tasks, task A, task B, and task C. The periods and the worst case execution time are given. So task A has a period of 80 clock ticks and it needs 16 clock ticks to finish executing. Task B has a period of 40 clock ticks and it needs 10 clock ticks to finish executing. And finally, task C has a period of 16 clock ticks and it only needs 4 clock ticks to finish executing. This question did not specify the arrival time nor the deadlines. Therefore, we will assume the default assumption for the arrival time that all three tasks arrived at the same time, which is clock tick 0. And regarding the deadlines, since the deadline is not provided, therefore we will go with the default assumption for deadlines that the deadline is equal to the period. Okay? And the question states, using the UB test, can we draw conclusions about the schedulability of the set under RM? So since here the deadline is equal to the period, we can use the utilization bound. As I stated before, the UB test, we cannot use the UB test if the deadline is different than the period. However, since the deadline is not specified in the question, the default assumption is deadline is equal to the period. Okay, therefore I can actually use the easy shortcut to check whether this set of tasks is schedulable under RM or not using the utilization bound test. Okay, and if you remember the utilization bound, it is the summation of the utilization of the tasks, and this summation must be less than or equal to n multiplied by 2 to the power of 1 over n minus 1. If we go and actually calculate the summation of the utilizations, the utilization of one task is the execution time or the computation time divided by the period. So here 16 divided by 80 plus 10 divided by 40 plus 4 divided by 16. Here we calculated the summation of the utilizations. The second part of the equation was to calculate n multiplied by 2 to the power of 1 over n minus 1, which is the threshold. And we told you before, n stands for the number of tasks. Since the system has 3 tasks, therefore 3 multiplied by 2 to the power of 1 divided by 3, all of this is minus 1, therefore it will be 0.779. And by the way, as I told you before, the threshold is related to the number of tasks. So the previous question, we had 3 tasks and we had the same threshold value, because to calculate the threshold value, we use the number of tasks. So any system with 3 tasks will always have the same threshold value, which is 0.779 for the rate monotonic utilization bound test. Okay, we want to see whether we met the condition or not. So 16 divided by 80 plus 10 divided by 40 plus 4 divided by 16, which is the summation of the utilizations, is equal to 0.7. Okay, 0 is 0.7 less than or equal to 0.779. Yes, it is less than or equal. Therefore, this set of tasks is 100% schedulable under RM. Remember the 3 scenarios? This maps to the first scenario, that the summation of the utilizations is less than or equal to the threshold. So 0.7 is actually less than or equal to 0.779. Therefore, this set of tasks is schedulable under RM. However, the other 2 scenarios were, just a reminder, the second scenario was that the summation of the utilizations is bigger than the threshold. However, it is less than or equal to 1. Therefore, we say that it is inconclusive. We do not know whether it will be schedulable or not schedulable. However, the third scenario is that the summation of the utilizations is larger than 1. We say that it is an overload and it will not be schedulable under any means. But here we fell under the first scenario. It is less than or equal to the threshold. Therefore, I can say 100% it is schedulable. If it did not fall under the threshold and it went to the second scenario, it's larger than the threshold but less than or equal to 1, there were 2 techniques. The simple technique, or actually it is not a simple technique, but there is a theoretical technique which is calculating the response time, which we'll be tackling later on in this tutorial, or as we did with the previous question, we drew the execution diagram. And using our own eyes, using observation, we found out that task A missed its deadline. Therefore, the set of tasks in the previous question were not scheduled. Because actually when we did the UB test, it stated it is inconclusive. It was larger than the threshold, but less than or equal to 1. So it was inconclusive. We drew the execution diagram. We found out that tasks B and C were scheduled properly. However, task A was not scheduled properly because it missed its deadline, which was equal to the period. Therefore, we said that this set of tasks is not schedulable under RM. However, in this example, question 2, it is schedulable under RM. Here it tells us draw the execution diagram in a window of 25 ticks of the above set using the RM scheduling. So now let's draw the execution diagram and move back to our sketchbook. As we all know, we have here 3 tasks, task A, task B, and task C. And since the question did not specify an arrival time all of them will arrive at T0, which is clock tick number 0. Okay, if we remember the properties of the task, we had task A with a period of 80 clock ticks and an execution time of 16 clock ticks. We had task B with a period of 40 clock ticks and an execution time of 10 clock ticks. And finally, we had task C with a period of 16 clock ticks and an execution time of 4 clock ticks. This is the worst case execution time, and we actually take into consideration the worst case. Let's move it to the side. And since the question did not specify the deadline, therefore deadline is equal to the period. Okay? Now we need to assign priorities to the tasks. For RM, the priorities are assigned according to the shortest period. So the task with the shortest period or the task with the shortest period will have the highest priority. Here, task C has the shortest period. It has a period of 16 clock ticks compared to the 40 clock ticks of B and the 80 clock ticks of A. Therefore, task C will have the highest priority, followed by task B, because task B has the second shortest period, which is 40 clock ticks, and finally the lowest priority will be given to task A because it has the longest period, which is 80 clock ticks. So if all three tasks arrive at the same particular time or the same exact time, then the task with the highest period will run, which is task C. So task C will run for 4 clock ticks. Let's draw here task C. It will run for 4 clock ticks, and it actually used 4 out of 4. So it finished execution because its worst case scenario or worst case execution time is 4 clock ticks, and it actually spent 4 clock ticks. Therefore, I must draw a downward line or a downwards arrow. Okay? So the upward arrow represents the arrival time. The downward arrow represents that a task finished its execution fully. Okay? Task C finished its execution, and it will return again to the system at clock tick number 16. So until it returns again to the system at clock tick number 16, we have 2 tasks remaining, task A and task B. A task needs to actually run. So which task will run? It will be task B, because task B has the second shortest period after task C, and since task C finished execution, therefore task B will start executing. We have here task B will start at clock tick number 4, and it actually needs 10 clock ticks to execute. So it will finish at clock tick number 14. Okay, so this is 14. Let's assume it is 14. And it spent 10 out of 10. It needed 10 clock ticks, and it spent 10 clock ticks from 4 to 14. And since it finished executing, we will represent it with a downwards arrow because it finished executing. Okay? Task B will return back to the system at clock tick number 40. Because from 0, it started at 0, or it arrived to the system, it arrived to the system at 0, then its period is 40, so 0 plus 40 is 40. After 40, it will arrive again at which clock tick? 80, because 40 plus 40 is 80. Okay, so we have task A remaining in the system, and since task A is the remaining task in the system, it will execute, and it will execute only for 2 clock ticks from 14 to 16. Why did it execute for 2 clock ticks instead of the full 16 clock ticks it needs? Okay, task A needs 16 clock ticks to finish executing. However, it will only execute for 2 out of the 16. This is because at clock tick 16, task C returned back to the system. Here we have task C returning back to the system at clock tick number 16. because it's a periodic task and its period is 16. So originally it arrived at clock tick 0, 0 plus 16 is 16. So task C, the new instance of task C, will return back to the system at clock 616. Therefore, when it returned back to the system at clock tick number 16, it preempted task A. Task A was executing and finished 2 clock ticks out of the 16. However, task C returned back to the system. Therefore, task C will preempt, will block task A, will stop it from executing, and it will start executing. So actually, as you can see here, we will start executing task C, and task C will execute for 4 clock ticks. 16 plus 4 is what? Is 20. Okay, and here it spent 4 clock ticks out of the 4 clock ticks. I mean, I could represent it much better in a smaller font. 4 out of 4. Okay, so task C has the highest priority in the system, therefore it executed and preempted task A. And here we will draw a downward line because task C finished execution. Okay, task C will return again to the system at what clock tick? At clock tick number 32, because it arrived at clock tick 16. 16 plus 16 is 32. Therefore, task C will return back to the system at clock tick number 16, at clock tick number 32. Okay, so how many tasks are remaining in the system? Task B is not actually ready. Task B will return back at clock tick 40. So we do not have any other task other than A. So A will continue executing. However, task A, which we use the green color for, will start executing from clock tick 20 to clock tick 32. Okay, so it started from 20 and it will remain to 32, which means it executed 14 out of the 16 execution or clock ticks needed to finish execution. Why did it stop at clock 32, not 34? I mean, if it needed 2 additional clock ticks to finish, so it should finish at clock tick 34. But however, task C returned back to the system at clock tick number 32. Here at 32, task C returned back to the system. Therefore, task A could not finish executing. It was preempted or blocked again by task C because task C returned back to the system. Okay, once task C returned back to the system, it will execute for 4 clock ticks from 32 to 36. Okay, here is 4 out of 4. And since it finished execution, we will draw what? The downwards arrow. Not here, we'll draw it here. Okay, so actually again, at clock tick 20, the instance of C finished execution. Okay, at this particular time in our system, the remaining task is A, because B will return at clock tick 40 and C will return back at clock tick 32. So from 20 to 32, task A was executing. Therefore, the total number of clock ticks taken by task A was 14 out of the 16. It needs 16 to finish executing. It's the worst case execution time. It was preempted at clock tick 32 by task C because task C returned back to the system at clock tick number 32. Therefore, task A did not complete the remaining or the needed 2 clock ticks to finish its execution. No, it was preempted by task C. Task C returned back to the system at clock tick 32. It executed for 4 clock ticks. It finished execution. Therefore, we drew a downwards arrow. And then at clock tick 36, how many tasks are remaining in the system? Only one, which is task A. Therefore, from 36 to 38, what will happen? task A will execute. So I have here from 36, okay, till 38. This is 36 and this is 38. What will happen? I could draw it here. We finished 16 out of 16 clock ticks. Okay, and now I can draw what? I can draw a downwards arrow because task C finished its execution. So as you can see, task A, I mean, finished its execution. So task C started at 32 and it needed 4 clock ticks, so it finished at clock tick 36. At clock tick 36, the scheduler will look at the remaining tasks ready to execute. We have only one task remaining because B will return back to the system at clock tick 40. It will return back at clock tick 40, and actually task C will return back at clock tick 48. Okay, 32 plus 16 is 48. So we have only task A remaining in the system. So it will execute. Task A only needed 2 clock ticks. So it will execute from 36 to 38. It used the remaining 2 clock ticks and it finished execution. Therefore, we drew a downwards arrow. From 38 to 40, because the upcoming task that will return back to the system will be task B. Task A will return back to the system at clock tick 80, and task C will return back to the system at clock tick 48. However, task B will return back to the system at clock tick 40. From 38 to 40, if we had an ideal task in our system, the ideal task will run. Okay? That's a rule of thumb. If we had an ideal task in the system, this ideal task will run. However, if our system does not have an ideal task, I mean, when we were talking about FreeRTOS, we stated that we have an ideal task. However, FreeRTOS does not use RM. It uses the priority-based time slicing mechanism, where you as a user assign priority to the task. Okay, and according to the assigned priority by you as a user, the scheduler will choose the tasks. And if 2 priorities are equal, we perform time slicing. However, FreeRTOS does not use rate monotonic. And FreeRTOS had an ideal task. So if you were for example, if you were in FreeRTOS, the ideal task will run from 38 to 40. However, if our system does not have an ideal task, the system that is implementing the rate monotonic algorithm, we do not know which system. However, if the system does not have an ideal task, nothing will occur. However, if the system had an ideal task, then the ideal task will run from clock ticks 38 to 40, because the ideal task usually has the lowest priority ever. Okay, so here we do not know whether we have an ideal task or not, so we did not draw the execution diagram of an ideal task. So from 38 to 40, we did not draw anything. Okay, now at clock tick 40, task B arrived back to the system, so it will run. Task B requires 10 clock ticks. However, it will not run for 10 clock ticks. It will only run for 8 clock ticks. It will stop at clock tick number 48. And here it executed 8 out of the 10. Why? Because at clock tick 48, task C returned back to the system. So here at clock tick 48, task C returned back to the system. And task C has the highest priority because it has the shortest period. Therefore, task B only executed for 8 clock ticks from 40 to 48. At 48, task C returned back to the system, preempting or blocking task B. And task C will run for the 4 clock ticks because its execution time is 4. So from 48 to 52. 52. Okay, 4 out of 4. And since it finished execution, we must draw the downwards arrow. Okay, then from 52 to 54, task B will continue executing. here from 52, this will be 52, and this will be 58. I only needed 54, I mean 52 till 54. I only needed 2 clock ticks. So from 52 to 54, this will be 10 out of 10. I finished executing task B, and I will draw a downwards arrow. Here, a downwards arrow. Okay, so at clock tick 52, task C will return back to the system at clock tick 64. Okay, however, there are no other tasks in the system except task B. Therefore, task B will run from 52 to 54 because it had only 2 remaining clock ticks. It already executed 8 out of 10. It had 2 remaining, so to execute 10 out of 10, it executed from clock tick 52 to 54, and it now finished execution. Okay, task C will return back to the system at clock tick 64. However, at this moment, at clock tick 54, I have 0 tasks in the system if there is no idle task. So I'm saying that if we have no idle task, we do not have an idle task from 54 to actually 64, we do not have any tasks in the system, so the system will not be executing. However, if we had an idle task, so from 54 to 64, the idle task will be the task executed. It depends on the system and the characteristics and properties of the system, whether we have an idle task or not. Okay, in this scenario, we only drew the execution of A, B, and C, and we do not know whether we have an idle task or not. Okay, so actually at clock tick 64, task C will return at 64, and it will execute for 4 clock ticks. So it will end at 68, and actually it executed 4 out of 4. Therefore, I need to draw a downwards arrow. And here is the downwards arrow indicating that this task finished executing. Okay. However, task A will return back to the system at clock tick 80 because it has a period of 80, and initially it arrived at 0. So 0 plus 80 is actually 80. Task B, it returned back to the system at clock tick 40. Therefore, it should return the next time at 40 plus 40, which is 80. And finally, task C arrived at the system at clock tick 64. Therefore, 64 plus 16, it means that it will arrive again at the system at clock tick 80. So all 3 of them will arrive again back at clock tick 80. If this is 80, task A will return, task B will also return, and task C will return, and we will repeat this the same exact cycle over and over again. Okay, so if we return back to our question, here is the graph in a better way, better than the one I drew. This is computerized. Since we did not have an arrival time, all arrived at clock tick 0, we do not have a specified deadline. The deadline was not specified in the question. Therefore, deadline is equal to the period. And when we did or performed the UB test, it was schedulable. The RM can schedule these tasks. And as you can see, from 0 to 80, all tasks were scheduled. And actually, at clock tick 80, all of them will again repeat the same cycle of arriving at clock tick 0, because all of them will arrive at clock tick 80. So this part will be repeated again after clock tick 80. However, between 0 and 80, we found out that all tasks finished executing all of their instances before their respective deadlines. So now let's move on to our third question and question 3. This is the response time equation learned in class. Okay, so the previous 2 questions, we used the utilization bound test or the UB test to determine whether a group of tasks is schedulable under RM or not. However, we had 2 problems with the utilization bound or the UB test. The first problem is that we can only use the UB test if the deadline is equal to the period. So if the deadline is not equal to the period, we cannot use the utilization bound test. The second problem is that if the UB test says that this set of tasks is schedulable under RM, then it will be 100% schedulable under RM. However, if the summation of the utilizations is larger than this threshold, but less than or equal to 1, then we are in an inconclusive state. I cannot determine whether it is schedulable or not schedulable. Therefore, we need to perform another check, which is the response time check, which will be tackling in this question. However, from the beginning, if actually the deadline is not equal to the period, then we need to use the response time immediately. However, using the response time, even if the deadline is equal to the period, we can use the response time because it will 100% inform me whether the set of tasks is schedulable under RM or not. However, since the UB test is much faster and is much easier, as you can see here, the response time equation is a complex equation. Okay, it will take a lot of time and effort to calculate. Unlike the UB test, we did it in seconds. It was a summation of the utilizations. Okay, so the response time equation takes a lot of time and effort, so they prefer using the UB test because if the UB test, when the deadline is equal to the period, and the UB test succeeds, it says it is schedulable, then it is 100% schedulable. However, if it is inconclusive, we need to perform further checks, and in this case, they will use the response time. But as I told you, you can use the response time from the beginning, even if the deadline is equal to the period, but it will take a lot of time and effort. As you can see here, the response time equation is actually a bulky equation. And the UB test is called sufficient but not necessary. So when we refer to the UB test, we call it sufficient but not necessary because the UB test can tell me whether, the UB test, if it succeeds, then it is 100% accurate about whether this group of tasks or set of tasks will be scheduled under RM or not. However, if it fails, it does not mean 100% that it cannot schedule these tasks. Therefore, it is sufficient that if it tells you it is schedulable, then it's 100% schedulable. But it is not necessary, meaning that if it tells you it is not schedulable, it does not mean that it is not schedulable. Therefore, we call it inconclusive. And therefore, the UB test is also known as sufficient but not necessary. Here, the response time is sufficient and necessary, meaning that if it tells me it is schedulable, then it is 100% schedulable. If it tells me it is not schedulable, then it is 100% not schedulable. Let's see the response time equation. Response time of I, and I is a task. We are trying to calculate the response time of the task, and as you will see, we actually calculate the response time of all tasks present in a particular set. Okay, so I is the task, maybe task A, maybe task B, maybe task C, is equal to the computation time of I, C of I. Okay, it's the execution time of task I plus the summation of J belonging to HP of I. Okay, so we have a set of other tasks called HP of I, and we are trying to calculate the summation of something related to them. Here we have the ceiling mark. So actually the value of Ri divided by T of J, we will seal this value. Ceiling means rounding up. Okay, R of I is the response time of task I, and T of J is the period of task J. So actually we have a set of tasks. HP of I results in a set of tasks, and we will be trying to calculate this for all of the tasks present in this set of tasks. Okay, ceiling of the response time of I over the period of J and multiplied by the computation time of J, or the execution time of J. Okay, so the first question, what is HP of I? As you can see here, J belongs to HP of I, and HP of I is a set of tasks. So we want to know what is HP of I. It is the set of tasks with priorities higher than or greater than task I. So actually, we are trying to calculate the response time of task I. HP of I, H stands for higher and P stands for priorities. So the tasks with higher priorities than I is the result of HP of I. So actually J belongs to HP of I, meaning that I am trying to find out all the tasks that have a higher priority than I. If you remember the previous two questions, we had three tasks, A, B, and C. Task C always had the highest priority. So actually, and while actually A had the lowest priority, so if I was trying to calculate the response time of task A, I will be A, so R of A equal to the computation time of A plus the summation of what? HP of I, meaning HP of A, all tasks with higher priorities than A, which were B and C, because both had higher priorities than A. So actually J once will be for B and the other time it will be for C. So actually we're gonna calculate the ceiling of R of A divided by T of B multiplied by C of B plus ceiling R of A over T of C multiplied by C of C. Okay, so HP of I donates the tasks with higher priorities than I. Okay, so here we have three tasks, task A, task B, and task C. However, the deadline is not equal to the period. We have a third column called relative deadline, and therefore the deadline is not equal to the period. For task A, we have a period of 5 clock ticks. So every 5 clock ticks, a new instance of task A will return back to the system. We have a worst case execution time of 1 clock tick. So it only needs 1 clock tick to finish executing. However, the relative deadline is 5 clock ticks. So actually it needs to execute during a window of 5 clock ticks from the moment it arrived to the system. Here, for task A, the relative deadline is equal to the period. However, it is not the case for task B and task C. Task B has a period of 9 clock ticks, so it will return back to the system every 9 clock ticks. It has a worst case execution time of 4 clock ticks, meaning that it needs 4 clock ticks to finish executing. However, the relative deadline is 8 clock ticks. So actually, from the moment it arrived to the system, it has a window of 8 clock ticks where it needs to finish executing during this window. If I miss the window of 8 clock ticks and I did not finish executing, therefore I will miss the deadline. However, my period is what? Is 9 clock ticks. So I will return back after 9 clock ticks. However, the window that I am allowed to finish executing in is 8 clock ticks. This is the deadline. From the moment I arrive to the system, I have 8 clock ticks to finish executing. If I miss 8 clock ticks and I finish after it, then I missed the deadline. Okay? Finally, task C has a period of 6 clock ticks, meaning that it will return to the system every 6 clock ticks. It has a worst case execution time, or WCET, of 2 clock ticks. So it needs 2 clock ticks to finish executing. Finally, the relative deadline is 4 clock ticks. So from the moment task C arrives to the system, it has a window of 4 clock ticks. It needs to finish executing during this window. So if its execution time is 2 clock ticks, I have a window of 4 clock ticks to finish executing 2 clock ticks. So actually, if I go to my sketchbook and I drew this, no, not this, just assume this is a task. Okay, this is task C. It arrived at clock tick 0 and it will arrive again at clock tick 6 and it will arrive again at clock tick 12. Okay, however, from 0 to 4, it must finish executing because 4 is the deadline. Okay, 4 clock ticks from arrival of the task is the deadline. So if it did not execute during this window and it only needs 2 clock ticks to finish execution. So from 0 to 4, if 2 clock ticks were not dedicated for this task, task C, to execute and I miss the deadline of 4 clock ticks, therefore what? Therefore, it is not schedulable. Although its period is 6, however, the deadline is 4. So if it actually met the deadline, and arrived back to the system at clock tick number 6. So by clock tick number 10, it must finish executing because 6 plus 4 is equal 10. So 4 clock ticks from the moment it arrived is 10. So it needs to finish executing before clock tick 10. Else it will not be schedulable and it will miss the deadline. Okay, so let's remove all of this and let's go back to our question. Is the above set of periodic tasks schedulable under RM? So the question did not specify which test to use. It is just asking whether it is schedulable under RM or not. However, since the deadline is not equal to the period, we cannot say what? We cannot say that, or we cannot actually use the UB test because the deadline is not equal to the period. So we need to use the response time from the beginning. So it's a tricky question. It did not specify which type of test to use. However, if you deduce or from your observation, since the deadline is not equal to the period, therefore I cannot use the utilization bound test and I must use the response. So this is a simple note regarding the response time equation. The RM utilization bound is not applicable because the deadline is not equal to the period in the set. Response time analysis test should be used here, which I told you that since the deadline is not equal to the period, we cannot use the UB test. Here it says that the ceiling of R of I over T of J represents the number of times each higher priority task J will execute during R. So actually R of I is what is the response time taken by task I. However, T of J is what the period of task J. And we told you that J belongs to HP of I. HP of I is higher priority tasks of I. Okay, so J is a higher priority task than I, and I'm trying to calculate the response time of I. So when I divide the response time of I over the period of J, it will tell me the number of times task J will execute during the response time taken by I. And as you can see here, I is duplicated. Okay, I'm going to actually go into details about the duplication. However, there is a reminder: the ceiling function gives the smallest integer greater than the fractional number on which it acts. Therefore, the ceiling of 1 over 3 is 1, of 6 divided by 5 is 2, and of 6 divided by 3 is 2. Because 1 divided by 3 is 0 point stuff, 0 point stuff sealed will be 1. 6 divided by 5 is 1 point stuff. 1 point stuff sealed will be 2, and finally 6 divided by 3 is also 1 point stuff. So actually we seal, we round up, so it will be 2. Okay, and this is the equation, the summation of J belonging to HP of I. J is a task that is has a higher priority than I. The ceiling of R of I over T of J, the response time of I divided by the period of J, meaning that how many times task J will execute during the response time of I, or during I, okay, or during R, the response time taken by I, which is R, multiplied by the computation time of J. This represents the interference from all higher priority tasks. So actually this part of the equation, which is the second part of the equation, represents the interference from all higher priority tasks. It actually checks how many tasks and what is the time taken for these tasks to actually preempt me as task I and stop me from executing because they have higher priorities than me, so they will preempt me and block me and will execute instead of me. So actually this part of the equation tries to figure out all of the tasks that will interfere with task I. How to solve the equation, you may ask? By forming a recurrence relationship. Okay, so if we go back, we had here R of I equals C of I plus summation ceiling R of I divided by T of J multiplied by C of J. As you can see, we have here R of I and we have here R of I. So I told you the duplication. How come can I use R of I and I'm actually calculating R of I? I do not know the response time of I. So how can I use this response time that I'm trying to calculate inside the equation? Hence, we form a recurrence equation. Okay, so it will be done through numerical analysis. Okay, it's like we'll be looping over and over again. Okay, we replace the r's with w's. So w of I n plus 1 is equal to c of I plus the summation of w of I of n over t of j multiplied by c of j. So you can imagine as if we are looping, okay? We are looping from index 0, where n at the beginning will be 0, and then every time we will be what? We'll be looping and looping again. So if n is 0, we will be trying to calculate w of 1 using the value of w of n, which is 0. And the next time, we'll be calculating w of 2 using w of 1, w of 3 using w of 2 result, etc. So you can imagine it as if it is looping. I know at this moment in the tutorial, you may feel it is complicated, but once we start solving, you will find out that it is very easy to calculate and everything is simple. But just the terminologies sound complex. Okay, here it says W of 0 is equal to C of I. So actually, the very first ever iteration we will be performing, we will just omit the second part of the equation, and we'll only have the first part of the equation, which is the C of I. And we are going to note it as Ri of 0 equal C of I. So actually, I'll be calculating Ri of 0, Ri of 1, Ri of 2, Ri of 3, etc. Okay? And definitely we'll be having a stop condition when we will stop looping. However, Ri of 0 means that n is equal to 0. Ri of 1 means that the n in the equation will be equal to 1, etc. Okay, when we will stop looping, we have two conditions. The first condition, we will stop looping if the response time is greater than the relative deadline. So if I have a response time that is greater than the relative deadline, I will stop looping and say that it is not schedulable under RM. However, the second condition for stopping the loop is that R of n minus 1 and R of n both result in the same exact value. So I looped for an iteration and I had the value or the response time equal x. I performed another iteration after it and I had the same exact response time, which is x. I had the same exact value. So when the last two values calculated from the last two iterations are equal, then I stop the loop and say it is schedulable under RM. So it will not be schedulable under RM if the response time is greater than the relative deadline. It will be schedulable under RM if the result of the last two iterations is exactly the same. Okay? So actually, let's start calculating the response time for each of the three tasks present in our system. And actually, as I told you, we will perform the response time calculation for each task. And if at least one task is not schedulable, then the entire set of tasks is not schedulable. Okay? However, if all three tasks are schedulable, this means what? That the set of tasks is schedulable under RM. If we go back, let's actually determine the tasks and their priorities. We have task A, task B, and task C. And the priorities are given according to the period, not the relative deadline. Take care. Okay? The priorities are given according to the period. The task with the shortest period will have the highest priority. Here we have task A, which has the shortest period. It has a period of 5 compared to task B, which has a period of 9, and task C, which has a period of 6. Therefore, task A has the highest priority, followed by task C having the second highest priority, and then task B will have the lowest priority because task B has the longest period. Okay, task A period is 5, therefore it is the smallest period, it's the highest priority. Followed by task C, which has a period of 6, which means that it has the second highest priority. Finally, task B, which has a period of 9, which is the longest period, therefore it has the lowest priority. And let's calculate the response time for task A. Although, if you are smart enough, you will deduce that Since task A has the highest priority, it will always run. So it will always be scheduled because it has the highest priority. Once it enters to the system and it arrives, it will execute and will kick or block or preempt any other task. Okay, so if we move back to the sketcher and we want to calculate the response time for task A, if we remember the equation, and let me write the equation here at the side, W of I of n plus 1 is equal to C of I plus the summation J belongs to H P of I. J is a task which has a higher priority than I. We have the ceiling of W of I of n over T of J, which is the period of J, okay, its ceiling, multiplied by what? By the computation time or the execution time of J. Okay, if we want to calculate actually the response time of task A, so how will it be? So if we recall the properties of our tasks, we had task A, which had a period of 5, it had an execution time of 1, and it had a relative deadline of 5. B had a period of 9, an execution time of 4, and a deadline of 8. And finally C, which had a period of 6, execution time of 2, and finally a deadline of 4. Okay, so this is the properties of our table. The first column is actually the period. I can actually write it. Here it is the period, which is T. The second column is C, the computation time, and the third column is D, which is the deadline. Okay, period, computation time, and deadline. If you want to calculate R of A of 0, since we are going to start with the highest priority task, okay, it is equal to C of I. So C of A is 1. The computation time of A is 1. Plus, as you can see, task A has the highest priority. Do we have a set of HP of I highest priority than A? No, this set is empty because we do not have any task that has a higher priority than A. A is the highest priority task. So always this second part of the equation will evaluate to 0, which is equal to 1. Okay, so the response time of A is equal to 1, which makes sense because task A has the highest priority in the system. So when it arrives to the system, it will block and preempt any other running task and it will start executing from the moment it arrives to the system. Therefore, its response time will always be equal to its computation time, which is 1, because it's the highest priority task. So it will always what? Kick any other task when it arrives and will execute for its computation time, which is 1. So if I try to actually calculate RA of 1, it will be what? The computation time, which is 1, plus this will also result in a 0. So 1 plus 0 is equal to 1. Therefore, RA of 0 and RA of 1, the result are the same. We stop the iteration and the task A is schedulable under RM. The task, not the set of tasks. A alone is schedulable under RM. We need to check for the other two tasks, B and C. Okay, but actually, as a rule of thumb, the highest priority task will always be schedulable alone because no other task will preempt it. As you can see, HP of A was always 0, was always empty. We did not have any task that has a higher priority than the highest priority task. Therefore, the second part of the equation, this part will always be 0. Okay? Therefore, the response time of the highest priority task will always be what? Will always be equal to its computation time. Okay? Now we are done with RA of 1 or RA in general, the response time of task A. The second highest priority task was C because it had the second shortest period, which is 6. Okay, so we need to calculate the R, or the response time of C. R of C at the beginning, here R of C of 0 will start the first iteration, is equal to the computation time of C, so it is 2, C of C is 2, okay, so it is 2 plus what? The summation of J belonging to HP of I. How many tasks have a higher priority than C? Only one task, which is A, because C is the second highest priority task. So the highest priority task is A. So in this part, J is equal to A. Okay? So we will try to calculate the ceiling of Wi of n. Did I have any previous response times? No. So it will be 0 over the period of J. The period of task A is 5. Okay, multiplied by the computation time of A, which is 1. Because here J is equal to A. Okay, so this part will actually be evaluated to 0, since 0 divided by 5 is 0, multiplied by 1 is 0, so R C of 0 is what? It is 2. Okay, so again, R C of 0 is equal to computation time of C, which is 2, plus the summation. Actually, I do not need a summation here because I only have one task that has a higher priority than task C, which is task A. So J is equal to A. Wi of n, I did not have any previous iteration. So at the beginning, the first iteration does not exist. So it's 0 divided by 5. T of j is 5. The period of task A, since j is equal to A, the task of period A is 5. The period of task A, I mean, is 5, multiplied by 1, which is the C of j, the computation time of task A. Let's move on to the second iteration. Our C of 1 is equal to the computation time of C, which is 2, plus J belonging to HP of I. We still only have one task which has a higher priority than task C, which is task A. Therefore, we do the ceiling of Wi of n. The previous response time from the previous iteration is what? Is 2. Therefore, this will be 2 divided by the period of J, which is the period of A, which is 5, multiplied by what? The computation time of A, which is 1. Okay, why is this 2? Because Wi of n, W of C of 0, n is 0, which is the number between the brackets. The previous response time was 2. 2 plus 0 is equal to 2. I can write it here if you want. It's equal to 2. Okay, so the previous response time was 2. So to calculate the next response time, I use the previous response time. So the previous response time was actually 2. So 2 divided by the period of task A, which is 5, multiplied by the computation of task A, which is 1. So it will be equal to 2 plus 2 divided by 5 sealed. It results in 0 point stuff, which will be 2, which will actually map to 1 or round up to 1, and 1 multiplied by 1 is equal to 1. So actually here, the response time is equal to 3. 2 divided by 5 is 0 point stuff. We seal it up, so it will be what? Instead of 0 point stuff, it will be 1. 1 multiplied by 1 is equal to 1. So 2 plus 1 is equal to 3. Is 3 greater than the deadline of task C? No, the deadline of task C is 4. And take care, this is what we perform after every iteration. Okay, in the very first iteration, we should have checked, is the result 2 greater than the deadline of task C, which is 4? No, it is not greater than. So I will continue iterating. I continued. Now, the second iteration, I had 3. I will first check, is 3 equal to 2? I'm going to check the last 2 iteration results, because if they are equal, then this task is schedulable. However, 3 is not equal to 2. Then I will check for the second condition. Is 3 larger than the deadline, which is 4? No, it is not larger than the deadline. So what? So I need another iteration. I will perform another iteration. Or a response time of C of 2 is equal to the computation time of C, which is 2, which is this value, plus the ceiling of the previous response time was what? Was 3. So 3, which is Wi of n, divided by the period of A, which is 5, multiplied by the computation time of A, which is 1, is equal to 3 divided by 5 is 0 point stuff. We seal it up, so it will be 1. 1 times 1 is equal to 1. So 2 plus 1, which is equal to what? Which is equal to 3. I'm going to check first. Is 3 equal to 3? The last two iterations. Is this 3 equal to this 3? Yes, they are equal. Therefore, task C can be scheduled alone with task A. So if my system has only two tasks, A and C, then RM can schedule both efficiently. Okay. However, my system has 3 tasks. Therefore, I need to calculate also the response time for the remaining task, which is task B. However, here the last two iterations resulted in the same exact values, 3 and 3. They are equal. Therefore, it is schedulable. If it was not, I was going to check the deadline. If it is larger than the deadline, it will be not schedulable. Else, I will perform what? Another iteration. So now I undoed all of the stuff I did to have a clean sketchbook. And as you can see, we checked for the response time of task A and it was schedulable. We checked for the response time of task C and it was schedulable. Now let's check for the response time of task B, which has the lowest priority. Okay, so if we draw here, no, I want the drawing. R B of 0 will be equal to the computation time of B, which is 4, plus the summation of J belonging to higher priorities of I. Higher priorities of task B are two tasks, A and C. So J will once be A and the second time it will be C, and we need to perform a summation on these two. However, the very first time, the response time of B at iteration 0, we do not have what? A previous response time. So actually this will result in a 0. So if we calculated it, 0 divided by the period of task A, which is 5, multiplied by the, let's do here a bigger bracket, multiplied by the computation time of task A, which is 1, plus, because it's a summation, we do not have any previous response time, divided by the period of task C, which is 6, multiplied by the computation time of task C, which is 2, and I close the bigger bracket. Okay, this will result in a 0. Why? Because I do not have any initial response times. The very first iteration, I do not have any response times. Okay, however, this part was the interference of task A to task B, and this part is the interference of task C to task B. Since task A and task C have higher priorities than task B, so any one of these two, if they arrive to the system while task B is actually executing, they will preempt and block task B. Therefore, we have here the summation of J belonging to higher priorities of I. So we have task A and task C that belong to this set of tasks that has a higher priority, or that have a higher priority than task I, which is task B. Okay, so here we will have finally a result of 4, because all of this will result in a 0. 4 plus 0 is 4. Is 4 greater than the deadline of task B? No, it is less than 8. Okay, so we are fine and we need to perform another iteration. RB of 1, the next iteration, will be the computation time of B, which is 4, plus here the previous response time was what? Was 4. So 4, which is Wi of n, the previous response time from the previous step, divided by, if I'm tackling task A, which has a higher priority than task B, so the period of task A is 5, multiplied by the computation computation time of task A, which is 1, and since we are performing a summation, we will have a plus because we have here a summation of all tasks that have higher priority than task I, which is task B, since I here is B, plus the previous response time, which is 4, divided by the period of task C, which is 6, multiplied by what we have here, a ceiling, multiplied by the computation time of task C, which is 2. Okay, and here we close the summation bracket. If you want to actually know the values, so 4 divided by 5 will be 0 point stuff, and 0 point stuff sealed will be 1. 1 times 1 will result in what? In a 1. Here 4 divided by 6 will be also 0 point stuff. It will be sealed to 1. 1 multiplied by 2 will be what? It will be 2. So 4 plus 1 plus 2 is equal to what? 4 plus 1. Or actually what will be performed first is 1 plus 2 is 3. 4 plus 3 is equal to 7. Okay, because we have an inner summation here, so it will sum the 1 and the 2 before summing it to the 4. So 1 plus 2 is 3, plus 4 is 7. We will check. Is 7 greater than the deadline? No, it is not greater than the deadline. Is 7 equal the previous iteration, which is 4? No, it is not equal to the previous iteration. So we need one more iteration. Our B of 2 will be computation time of I, which is the computation time of B, which is 4, plus we start the summation. The tasks that has a higher priority a higher priority over task B, which are task A and task C. Okay, the previous iteration we had a result or a response time of 7. So 7 divided by the period of task A, which is 5. Okay, all of this will be sealed, multiplied by the computation time of task A, which is 1, plus another seal. The previous response time was 7, divided by the period of task C, which is 6, sealed, multiplied by the computation time of task C, which is 2. And we close what? The summation. So 7 divided by 5 will actually result in 1 point stuff. We seal this number up, then it will be 2. 2 multiplied by 1 is 2. Okay, 7 divided by 6 will also result in 1 point stuff. We round it up, it will be 2. 2 multiplied by 2 is 4. So 2 plus 4 is what? 6. 6 plus 4 is what? Is 10. Okay, so 2 plus 4 is 6, and 6 plus 4 is 10. So we have here 10. We check. Is 10 equal to 7? No, it is not equal to 7. We check the last two iterations, they are not equal. So is 10 greater than the deadline, which is 8? Yes, it is greater than the deadline. So it is not schedulable because the response time of this iteration resulted in a value that is greater than what? Greater than the deadline, meaning that I will miss my deadline, so it will not be scheduled. Okay, hence we stop, and since task B is not schedulable, therefore the entire set of tasks the entire set of tasks containing A, B, and C is not schedulable under RM. So all of this will not be schedulable under RM. I could be cool using the red. It is not schedulable under RM. Okay, and as I told you, the response time equation takes a lot of time. So they use the UB test as a shortcut if the deadline is equal to the period. However, if the deadline is not equal to the period, we need to use the response time, or even if I use the utilization bound on a set of tasks where the tasks or the period or the deadlines were equal to the period, but actually the summation of the utilizations was greater than the threshold but less than or equal to 1, then it will be inconclusive. So I need to also perform what? I need to also perform the response time equation. So if we go back to the slides, we'll have the solution. Here, task A had the highest priority, so it was always having a response time of 1, which is equal to its computation time, which is less than or equal to its deadline, so it was scheduled. Then we started with the second highest priority task, which was task C. Only task A had an interference with task C, so actually the set HP of I only had the task A. Okay, because task A is the only task that interfered with task C. We calculated its response time and we found out that the last two iterations resulted in the same value 3 and 3. Therefore, we stopped and it is schedulable since 3 was less than the deadline of task C. If you want to know the deadline of task C, it was 4. So 3 is definitely less than 4. Okay, the worst case response time of J of C is 3, since R is less than DC, which is equal to 4, or less than or equal. Okay, finally, we tried to schedule task B, which had two tasks interfering with it, since task B had the lowest priority and task A and task C had higher priorities than B. So we actually performed the response time calculation, and the set HP of I had two tasks, had the task A and had task C. So we had to actually calculate the summation of this part and then add it to the computation time of task B. However, at the end, we found out that one of the iteration resulted in a response time of 10, which was greater than the deadline of task B, which was 8. So task B had a deadline of 8. However, one of the iterations resulted in a value of 10. So we stopped, and therefore the entire set of tasks were not schedulable under RM. So now we are done with the rate monotonic algorithm, which is a static priority scheduling algorithm. What is the meaning of a static priority scheduling algorithm? It means that the priorities are fixed. Okay, if I have a set of 3 tasks in the system and their periods are defined, for the rate monotonic, we use to assign priorities according to the periods. Okay, the task with the shortest period will have the highest priority. Every time an instance of this task returns to the system, it will have the same exact priority, which is the highest priority. So all instances of the same task will be given the same priority, the same fixed priority. Okay, because what? This task has the shortest period. Having the shortest period for the rate monotonic algorithm means that you have the highest priority. Therefore, like question 1 and question 2, when task C had the shortest period, it had the highest priority. So every time a new instance of task C returns to the system, it is given the highest priority and it blocks or preempts any other running task and it will run instead of it. Okay, so this is the concept of static priority. Priorities will not change during execution. The instances of the same task will always have the same priority because they are determined, or the priority is determined on a fixed parameter, which is the period. And the period will not change. A period of a task will not change. Therefore, all instances of this task will be assigned the same period. However, there is a second paradigm for scheduling algorithms, which is the dynamic priority scheduling algorithms paradigm. We will be tackling one example, which is the earliest deadline first scheduling algorithm, also known as the EDF algorithm. And since it's a dynamic priority scheduling algorithm, therefore the instances of the same task may be assigned different priorities, because here the priority can change during execution. Okay, it is now depending on a variable. Okay, it's a parameter that we are going to use to determine the priority is not a fixed parameter, it's a variable parameter. Okay, and also the earliest deadline first is an optimal dynamic priority scheduling algorithm. And if you remember the keyword optimal, when we talked about the rate monotonic being an optimal static priority scheduling algorithm, we said that if any other static priority scheduling algorithm can schedule a group of tasks, therefore the rate monotonic can also schedule the same particular group of tasks. Same here for the EDF, however, it's an optimal for the dynamic priority scheduling algorithms. Okay, so this means that if there is any other dynamic priority scheduling algorithm that can schedule a set of tasks, therefore the EDF can also schedule the same exact group of tasks. Therefore, the EDF is optimal in terms of dynamic priority algorithms, and the rate monotonic is optimal in terms of static priority scheduling algorithms. How does the EDF work? It is simple. The task with the nearest deadline will be assigned the highest priority. So actually here, the priorities are assigned according to the deadlines of the tasks and their instances. Therefore, if I have 3 tasks in the system, the task with the nearest deadline will be assigned the highest priority. So here we depend on what? On deadlines. When is the deadline? If your deadline is the nearest one, then you will be assigned the highest priority and this task will execute. Okay, so that's why it's a dynamic priority scheduling algorithm, the EDF1, because deadlines deadlines may differ during execution. Therefore, the priorities can change during execution, and we'll be seeing an example right now on how does the deadlines differ during execution and how does the EDF assign priorities, and these priorities change according to the upcoming deadlines and what are the next deadlines, the nearest deadlines, etc. Okay, so our last question, question 4, we have 3 tasks. Task 1, Task 2, and Task 3, and you are given the period and the worst case execution time. And here, since the question did not state an arrival time, therefore we use the default assumption that all tasks arrived at the same instance, which is clock tick 0. The second statement is that the question did not state the deadline for the tasks. Therefore, the deadline for the tasks will be equal to the period of the tasks, because the question did not state the deadline of each task. So automatically the assumption is deadline equal period. Task 1 has a period of 4 and an execution time of 1. Task 2 has a period of 6 and an execution time of 2. And finally, task 3 has a period of 8 and an execution time of 3. Since we are using the EDF algorithm, the task with the highest priority will be the task with the nearest deadline. So here from this table, I cannot actually determine which task will have the highest priority at a given instance. I will only know that at instance 0, at clock tick 0, the task with the shortest or the nearest deadline will be task 1, because deadline is equal to the period, which is 4, compared to 6 and 8. So at clock tick 0, task 1 will have the highest priority. However, this does not mean that in the upcoming clock ticks, task 1 will also have the highest priority, and we will be seeing why, or we will see why. So the first question, using the UB test, the utilization bound test, can we draw conclusions about the schedulability of the set under EDF? So here, since the deadline is equal to the period, we can use what? We can use the UB test. Okay, however, the UB test for the EDF is different than the UB test for the RM, because the EDF can use 100% CPU utilization. So as you can see, the condition is the summation of the utilizations is less than or greater to 1. 1 means 100% CPU utilization. Therefore, here we do not have an inconclusive condition. And here actually, since the utilization is less than or equal to 1, this means that we can use 100% of the CPU utilization, or the EDF algorithm can actually tackle 100% CPU utilization. So here, the UB test will tell me whether it is schedulable or not schedulable. Okay, so we do not have the inconclusive part we had for the rate monotonic. So yes, take care. The condition here, the UB test for the EDF is different than the UB test for the rate monotonic. The rate monotonic, it was not less than or equal to 1. It had a calculation using the number of tasks present in the system. It was the number of tasks multiplied by 2 to the power of 1 divided by the number of tasks minus 1. Here we have what? we have less than or equal to exactly 1. So if you want to calculate the utilization of the previous tasks, utilization is the computation time divided by the period. So for task 1, 1 divided by 4 plus 2 divided by 6 plus 3 divided by 8. We calculated the summation of all three utilizations. 1 divided by 4 plus 2 divided by 6 plus 3 divided by 8. This will result in 0.95. 0.95 is actually less than or equal to 1. Therefore, this set of tasks is schedulable under earliest deadline first or under EDF, because the summation of the utilizations is less than or equal to 1. So it is schedulable under EDF. The second question, draw the execution diagram in a window of 24 clock ticks of the above set during or using the EDF scheduling algorithm. So actually now we want to draw the execution diagram of our three tasks. If we go back, we will find out that we have three tasks, task 1, task 2, and task 3. We have their periods and we have their execution time. We will need this info to actually draw what? The execution diagram. So if we go to our sketchbook, we have here the three lines, and since the question did not specify the arrival time of the tasks, all of them, we assume all of them arrived at what? At T0 or at clock tick 0. So here is task A, here is task B, we can draw B better, and finally here is task C at clock tick 0, and we draw an upwards arrow to represent the arrival of a task. Also, we need actually to know the properties of the tasks. So task A has a period of 4 and an execution time of 1. Task B has a period of 6 and an execution time of 2. And finally, task C has a period of 8 and an execution time of 3. We click OK, and we can move this to the side. Okay, so we are using the earliest deadline first algorithm, which means that the task with the nearest deadline will be assigned the highest priority. It's different than the rate monotonic. Do not get confused. Okay, so to understand how to actually know when is the nearest deadline, we need to initially draw the arrival time of all tasks, because in this question a deadline was not specified, therefore the deadline is equal to the period. So actually I need to draw the deadlines, which are the arrival times, because the deadline is equal to the period of all the tasks through the window of 24 clock ticks that was stated in the question. The question wanted us to draw the execution diagram in a window of 24 clock ticks, so we can actually visualize and observe the deadline of each task. So actually, if we take or look at task A arrived at clock tick 0, therefore it should arrive again. Its period is 4, so 0 plus 4 is 4, so it should arrive again at 4. Let this be 4. 4 plus 4 is 8, so it should arrive again at 8. 8 plus 4 is 12, so it should arrive again at 12. Here, let this be 12. 12 plus 4 is 16, so it should arrive back at 16. 16 plus 4 is 20, so it should arrive back at 20. And finally, 20 plus 4 is 24, so it should arrive back at 24, which is the end of our window. So task A has a period of 4, therefore we drew the expected arrival time of this task again to the system every 4 clock ticks. Okay, why did we do this? Because we are using a dynamic priority scheduling algorithm. So I need to actually understand how the priorities will change during execution. So to have an overview, I need to draw the deadlines. And since here the deadlines is equal to the periods, therefore I need to draw the arrival time, which is the period. Okay, for task 2, which I call task B, I don't know why, but task 2 is task B. It has a period of 6. So initially it should arrive again here. This is 6. Okay, 0 plus 6 is 6. 6 plus 6 is 12. So it should arrive again here. Okay, 12 plus 6 is 18, so it should arrive here in the middle. Okay, and 18 plus 6 is 24. Okay, so we drew the arrival time or the expected arrival time of task 2, which is task B. Because the question stated it is task 1, 2, and 3. However, I named them A, B, and C. But A is 1, B is 2, and C is 3. Finally, we have task C, which is task 3, has a period of 8 clock ticks. So 0, initially it arrived at 0, 0 plus 8, it will be 8. Okay, 8 plus 8 will be 16. And finally, 16 plus 8, it will be 24. And we want to start the execution diagram. Initially, I could choose a different color, for example, gray. We have task A, we have task B, and we have task C. I want to assign priorities using the earliest deadline first, or the EDF algorithm. The EDF algorithm assigns priorities based on the deadlines. The nearest deadline, or the task with the nearest deadline, will have the highest priority. So initially at time 0, we had 3 tasks in the system, A, B, and C, or 1, 2, and 3. Okay? So we will check the deadline of each task. The deadline of task A is at 4, the deadline of task B is at 6, and the deadline of task C is at 8. So which task will run first? It will be task A. So task A will run first, and it will run for 1 clock tick because its execution time is 1. So it will run for 1 clock tick from 0 to 1. This is 1, and actually it ran 1 out of 1. Okay, and since it finished execution, we must draw a downwards arrow to say that it finished execution. Okay, so here we at clock tick 0, we had 3 tasks. To determine the priority, which one of them will execute first, we look at their deadlines. Task A deadline is at 4, task B deadline is at 6, and task C deadline is at 8. So the smallest or the nearest deadline is what is task A, which is at 4 or clock tick number 4. Therefore, task A ran for its execution time, which is 1. So it ran for 1 clock tick, and therefore we drew a downward arrow representing that this task finished its execution. Now we have 2 tasks remaining in the system, task B and task C. We will check their deadlines. Task B will finish at its deadline is at clock tick 6, and task C has a deadline at clock tick 8. Which is the nearest deadline? It is 6. So starting from clock tick 1, which is here, I'm going to actually execute for 2 clock ticks because the execution time for task B is 2. So from 1 to actually 3, I will execute, or let me draw it with black. So here, or let's choose blue. So here we have clock tick 1. Okay, at clock tick 1, task B will start and it will execute for 2 clock ticks. So from 1 to 2 and from 2 to 3. So till here. Okay, and we must draw a downwards arrow to represent that this task finished its execution, and also we need to write that it was executed for 2 clock ticks out of the needed 2 clock ticks. So actually task B needed 2 clock ticks to execute, therefore it executed from clock tick number 1 to clock tick number 3. Okay, now we are done. Which task has the nearest deadline? Task C. Its deadline is at clock tick number 8. And actually, at clock tick number 3, I only have 1 remaining task in the system, which is task C. Therefore, it will automatically run because no other task is present in the system. So task C will start executing from clock tick 3. However, it will stop here at clock tick 4. Why? Because at clock tick number 4, task A returned to the system. So I'm going to check the deadline of task A and the deadline of task C, which is running. Task A will finish at clock tick 8, or its deadline is at clock tick 8. I mean, it will not finish. I mean, its deadline is at clock tick 8. And task C deadline is also at clock tick 8. So both have the same deadline. However, the system or the real-time operating system or the scheduling algorithm in particular will continue executing the current task that is running. So if I have two tasks having the same deadline, however, I'm already executing one of them, then the scheduling algorithm will continue executing this one. It will not perform a context switching, okay? Because context switching will waste time. Therefore, it will continue executing till it arrives at what? At clock tick number 6. Okay? It only needed what? It only needed 3 clock ticks. So it used 3 out of 3. And we draw what? We draw a downwards arrow, indicating that task C finished execution. So take care. Initially, at clock tick number 3, I only had one task in the system, which was C. So C started to execute, and it needed 3 clock ticks. However, at clock tick 4, task A returned back to the system. So the scheduling algorithm will check the deadline of task A and task C. Surprisingly, task A and task C both have the same deadline, which is clock tick 8, or which is at clock tick 8. Therefore, the scheduling algorithm will continue choosing the task that is already running to prevent loss of time due to context switch if it switched to task A. So since both have the same deadline, 8 and 8, it will continue executing the running task, which was task C. So task C executed till it reached clock tick 6 and it finished execution because it only needed 3 clock ticks from 3 to 6. Okay? Now we have what? At clock tick 6, task B returned back to the system. However, I have task A. We will check the nearest deadline. Task A has a deadline of 8 and task B has a deadline of 12. So which is the nearest deadline, 8 or 12? It is 8. So starting from clock tick 6, I'm going to execute task A for one clock tick, which is till 7. So I executed this for one clock tick, and I need to draw what? I need to draw the downwards arrow. Okay, because at clock tick number 6, I had two tasks in the system, task A and task B. Task A has a deadline at clock tick 8 and task B has a deadline at clock tick 12. So the scheduling algorithm will choose task A to run because it has the nearest deadline. And task A execution time is 1, therefore it ran for one clock cycle. Okay, so at clock tick number 7, because this is 7, I will try to run another task. So the only task present in the system is task B. So task B will start to execute. However, it will execute for one clock tick from 7 to 8. Because at clock tick 8, we have what? We have two tasks returning back to the system. Task A returned back to the system and has a deadline of 12, and task C returned back to the system and has a deadline of 16. However, task B also has a deadline of 12. So we omit task C because task C deadline is later. However, task A and task B both have the same deadline, which is what? Which is 12. However, since I was already executing task B, I will continue executing the running task, which is task B. I will not perform any context switching. Therefore, task B needs only 2 clock ticks, so from 7 to 8 and from 8 to 9. And this will be clock tick number 9. And it executed 2 out of 2. And we will draw what? We will draw a downwards arrow because it finished executing. So also task A and task B had the same deadline. However, task B was the one already running, so we will not context switch, or we will not actually kick task B out. No, we let it continue executing because it is the one executing and it has the exact same deadline as task A. So the deadlines are equal. Therefore, the scheduling algorithm will be like, or will say, I'm going to continue executing the already running task. Okay, this is at clock tick what? At clock tick number 9. We have at clock tick number 9, we have two tasks in the system, task A and task C. However, task A has a deadline of 12 and task C has a deadline of 16. Therefore, the scheduling algorithm will choose task A to run. So actually, I'm going to choose task A because its deadline is the nearest. So at clock tick number 9, I will run for one clock tick which is 10. So here 1 out of 1. Okay, and we need to draw a downwards arrow. So actually here at clock tick number 10, task A finished executing. How many tasks are there remaining in the system? We only have one task, which is task C. So task C will automatically run starting from clock tick number 10, and it needs 3 clock ticks to execute. So from 10 to what? Let me change the color. From 10 to 12, it will stop at 12. Okay, so here it executed 2 out of the 3. However, at clock tick number 12, 2 tasks returned back to the system, task A and task B. We are going to check the deadlines of all 3 tasks now present in the system before letting task C uh, continue the last clock tick needed. Task 12 has a deadline of 16. Task A has a deadline of 16. Task B has a deadline of 18, and task C has a deadline of 16. So we omit B because B has a later deadline. A and C have the exact same deadline. However, task C was the already executing task. Therefore, what? Therefore, it will continue till clock tick 13. And here is 13, and it ran for 3 out of 3, and we draw the downwards arrow. Why did the scheduler choose C over A? Because C was the already running task. So since both have the same deadlines, the scheduler will choose the task that is already running to prevent any loss of time during the context switch if it switched to task A. Okay, now we have in the system 2 tasks, task A and task B. We will check the deadlines. Task A deadline is 16, task B deadline is 18. So at clock tick 13, the scheduler will choose task A, not task B, because task A has the nearest deadline and it will run for 1 clock tick, which is from 13 to 14. Okay, actually I could use green. Okay, from 13 to 14, it was 1 out of 1 because the execution time of task A is 1, and we draw what? We draw a downwards arrow at 14. Okay, so here we have how many tasks remaining in the system? At T14, we only have one task remaining in the system, which is task B. So task B will execute, and it needs 2 clock ticks to execute according to the table. So it will run from 14 to 16. From 14 to 16, 2 out of 2. And since it finished execution, we must draw a downwards arrow. Okay? So at clock tick 16, 2 tasks returned back to the system, task A and task C. Okay? So actually, we will check their deadlines. Task A has a deadline at 20, and task C has a deadline at 24. So the scheduler or the scheduling algorithm will choose the nearest deadline, which is 20. So task A will execute for its execution time, which is 1 clock tick from 16 to 17. Okay. Here 1 out of 1, and we must draw what? The downward arrow to actually indicate that this task finished running or finished execution. Okay, at clock tick 17, I have one remaining task in the system, which is what? Which is task C. So actually here at clock tick 17, I have task C remaining in the system, so I will execute task C for 3 clock ticks. It's red. However, after executing the first clock tick from 17 to 18, and I still have 2 remaining clock ticks. However, at T18 or at clock tick 18, task B returned back to the system. So I'm going to check the deadline of task B and task C. B's deadline is 24 and C's deadline is 24. So I'm going to continue executing what? The current task, since the deadlines are equal. So to prevent any context switching and loss of time, I will continue executing the actual task that is in the running state. So here from 17 to 20. 3 out of 3, and I must draw a downwards arrow. Okay? Here at clock tick 20, I have two tasks in the system. Task A returned back at clock tick 20, and task B was already in the system. And both have the same deadline, 24 and 24. So actually here, the scheduler will choose one of them at random, because actually the deadlines are equal. Both have the same deadlines, 24 and 24. So the scheduler will choose a task randomly. Let's assume the scheduling algorithm chose task B. So here at 20, task B will what? Will run for 2 clock ticks from 20 to 22, 2 out of 2, and we draw what? We draw a downwards arrow. However, as I told you, let me draw it using a black arrow. Okay, so as I told you, at clock tick 20, I only had two tasks in the system, task A and task B. Task A arrived at clock tick 20, and task B was already present from clock tick 18. When we checked the deadline, both had the same deadline. So actually, any one of them can be chosen by the scheduling algorithm, because both have the same deadline and no one of them was already running, so I'm going to continue its execution. No, I'm going to start the execution of either task A or task B from the beginning. Therefore, the scheduling algorithm chose randomly, and we chose task B. We could have easily chosen task A, but we chose task B. But I mean, this part was chosen randomly. Okay? At clock tick number 22, I only have one remaining task in the system, which is task A. So it will execute for what? It will execute for one clock tick from 22 till 23. 1 out of 1. And I must draw what? I must draw a downwards arrow. Okay, and then all of them again will reappear to the system at clock tick number 24. So this execution diagram will be repeated again starting from clock tick 24, because all three tasks will arrive again, or three will be present together again starting from clock tick 24. Okay, so as you can see here, the earliest deadline first had dynamic priorities. The dynamic priority was assigned according to the nearest deadline. The task with the nearest deadline will get to execute. Okay, so it was not a fixed or a static priority algorithm. I 100% sure that once task X returns to the system, it will execute. No, here it is dynamic. The priority is actually changed during the execution of the tasks depending on our parameter, and for the EDF algorithm, the parameter is the deadline. The task with the nearest deadline will execute first. Okay, so here each instance of the task was given a different priority from the previous and the next instance. Okay, so if we return back to our question, this will be the neatly designed execution diagram. And as I told you before, it's really important for dynamic priority scheduling algorithms like the EDF to draw the deadline and the period of the tasks. So you can see the period will actually tell you the arrival time. So you need to draw the arrival time of the tasks, and you also need to draw the deadline so to know which task has the nearest deadline. In our case, the arrival time was equal to the deadline, since the deadline is equal to the period. So we only draw the arrival time, which is also the deadline. However, if the deadline was not equal to the period, therefore I had to draw the arrival times in order to what? In order to calculate the deadline, because the deadline is relative to the arrival time. If, for example, I have a task that arrives every 6 clock ticks and has a deadline of 4 clock ticks, so every time it arrives to the system, I need to calculate this arrival time plus 4 to determine what? The deadline. Okay, but since this case deadline was equal to the period, we only drew the arrival times, which represented also the deadline. And in this case, once we draw all of the arrival times and deadlines of all tasks, we start to execute starting from clock tick number 0. So now I can visually observe when is the nearest deadline using my eyes, and accordingly determine which task get to be executed at a particular clock tick. Okay? Now we are done with the tutorial. If you have any question, don't hesitate to post your question on Piazza. Stay safe and goodbye.